Welcome to today's webinar. Today we show you how you can design welds in our section 1. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, the newsletters, and customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Sonja von Bloh will be the presenter. She is responsible for the cross-section program, our section, and the add-on aluminium design, and she works also in the customer support team. Okay, how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and then I will receive your question and I will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Sonja. Sonja, it's your turn.
Thank you for the kind introduction. I would also like to warmly welcome you to today's webinar. In this webinar, I will demonstrate how a welded cross-section can be modeled in our section. I will explain how fillet welds are represented in our section and how this affects the calculation results. Additionally, I will go over the required settings for performing a weld stress analysis. The presented I section featuring a welded reinforcement and welded lips on the top flange will be modeled in our section. During this process, the types of fillet welds available in the program will be introduced. The throat welds are modeled using a standard fillet weld. The connection between the reinforcement plate and the flange is created using a lap fillet weld, while the lips are attached to the flanges via corner fillet welds. To begin, I create a new file in our section. I name this file example1. Since weld stresses can only be calculated using the analysis method thin wall analysis, I select this option. For the material, I choose steel S235. This material is already inserted in this file, but if you would need another material, you can choose this from the material library. I insert the I section to be modeled from the cross-section library. I use the section type parametric thin walls since this section type allows me to define the parameters of the cross-section manually. For the welded cross-section, I choose also the manufacturing type welded. I then define the dimensions of the cross-section. The height is 300 millimeter, width is 300 millimeter. The thickness of the web is 10 millimeter. The thickness of the flanges is 20 millimeter. At this point, welds could already be defined, but I deliberately postpone the step in order to demonstrate later how to create welds and what settings must be considered. When inserting the cross-section, I disassemble it into its individual components to allow for further editing. To ensure that the force transfer occurs exclusively via the weld and not through adjacent elements, a separation joint must be defined on the welded element. Let me explain this in more detail. In this example, the web is welded to both the top and bottom flanges. In this case, the web is considered the welded element. Therefore, separation joints must be applied at both the beginning and end of the web, in other words, at its connections to the flanges. If, on the other hand, the two right-hand flanges were to be welded to an existing new section, the separation joints would need to be defined on the flanges, as they would then be the welded parts. The separation joint is defined directly within the corresponding element. In this case, I open the Edit dialog of the web, and here I define the separation joint on start and end of the element. For verification, the separation joint is also shown graphically in the model. Next, I define the fillet welds. For this, I use the weld type fillet weld. First, I define the throat thickness. This should be 10 millimeter. Then I select the elements to be connected by the welds. These are the upper flanges to the web and the lower flanges to the web. The connection between the flange and the web is made via the fillet welds. I would now like to show in detail how these welds are represented. To do this, I examine the connection between the web and the top flange. The previously defined separation joint on the web ensures that there is no direct connection between the web and flange. Force transmission takes place exclusively through the weld. The program generates the connection elements shown in green, which represents the fillet weld. This configuration results in a closed cell, which leads to a breadth torsional moment of inertia being taken into account in the cross-section properties. The welds have a noticeable effect on the stress distribution. For comparison, I create an additional file with identical cross-section but without welds. I name this file example2. I choose here once again the analysis method, thin wall analysis. I use the material S235 and I define the I section with the help of the cross-section library. Here I choose the section type parametric thin-walled, the manufacturing type welded, and I define the dimensions of the cross-section, height 300 millimeter, width 300 millimeter, thickness of the web 10 millimeter, thickness of the flanges 20 millimeter. I insert the cross-section with OK and explode. To directly compare the cross-section properties and stresses, I display both models side by side, and for this I use here this function tile vertically. Then I start the calculation in both files. As already explained, the torsional constant in the file with weld is higher because of the additionally considered Brad torsional moment of inertia. Here I have a torsional constant of 195, and in the file without welds I have a torsional constant of 162. I then compare the unit shear stresses due to torsion. For this, I activate here the unit shear stresses in both files, and I choose here the type of display off, and also in this file. In the region of the closed cell, due to the welds, higher torsional shear stresses are observed in the welded section, while lower stresses occur in the remaining areas of the cross-section. To further reinforce the eye section, a flat steel bar is welded to the top side of the flange. I select a flat steel profile from the section library. For this, I open the navigator data and insert a new section, a flat bar. I want to define the dimensions manually, and I want to define here a width of 200 millimeter and a height of 50 millimeter. In the graphic preview, I set the center of the bottom edge of the flat steel as the reference point. I then select the insertion point in the working window, which corresponds to the center of the top flange. After confirming with OK and explode, the flat steel bar is placed centrally on the top of the flange. The connection between the flange and the reinforcement is made via a lap fillet weld. This type of weld provides a direct connection between both components, making additional connection elements unnecessary. Lap fillet welds are suitable for elements that run parallel to each other and make contact at least one point. So I open the lap fillet weld dialog, and here I define first the throat thickness of 5 millimeter. The first element to be selected is always the one whose front face the weld will be applied to. And this is here, this element on the top. As soon as the mouse hovers over the second element, a preview of the weld appears on the working window. Clicking on the second element completes the creation of the welds. On the right-hand side, I do the same, but I see here that the weld is not placed as intended. This is due to the graphical input method, where the first weld is automatically placed at the start. Only a second fillet weld on the same element would be generated at the element's end. To correct the weld's position, the orientation of the first element can be reversed. I will do this here in this file. I select here reverse element orientation, and now the weld is on the correct location. You have an alternative way to do this. For this, I undo this action. You have also the possibility to define the position in the weld dialog, and here you can choose the weld position at end of first element. To further reinforce the top flange, additional lips are welded to the sides. For this, I select a flat steel profile from the section library. So I open the section library again. I choose here bar sections, convert into parametric section, and then I define here the width. And the width should be 60 millimeter and the height 15 millimeter. I have now to rotate this cross section, and I do this in the step section location rotation mirroring, and I define here the rotation about x-axis, about 90 degrees. In the graphic preview, I set the upper right corner of the profile as the reference point. So I click here on this point with the mouse. The insertion point is then selected as the lower left corner of the top flange in the working window. And the cross section will be inserted with OK and explode. The inserted lip is then copied to the right-hand side. To do this, I select the component, and then I choose the Move Copy command. In the dialog that opens, I activate the checkbox Create Copy, and then I define the displacement vector. And click on OK. The connection of these parts is made directly using a corner fillet weld, meaning no additional connection elements are required. The only requirement is that the elements must touch at least one point. So I open here the corner fillet weld dialog. I define a throat thickness of 5 millimeter, and then I select the elements to be connected. The elements are selected one after the other using the mouse. The order of the selection does not matter. So I select here these elements. The welded cross-section is now fully modeled. The next step is to perform the weld stress checks. For this, a new load case must be defined. So, in the navigator data, I create a new load case and I define the load case name design. Within this load case, I define the relevant internal forces. So I open here in this load case the internal forces dialog. and I specify a shear force about 150 kilonewton. The selection of the weld stress components to be calculated is done in the weld stress configuration dialog. You find this dialog via the navigator data. Here under stresses, stress configuration, weld stress configuration. Here you can choose the stresses to calculate, and here it's also possible to define the limit stress types. The limit shear stress is calculated automatically, but it's also possible to define the limit shear stress user-defined. I leave the default settings unchanged, so I click here on OK. I then start the calculation. The weld stress results are displayed both graphically and in tabular form. The graphical results are located in the navigator results under weld stresses, and here I have to use the type of display isobands. And then you see here in the stresses directly the weld stress values. The tabular results can be found as a subtable under analysis of thin wall structures. So it's here this subtable weld stresses. This table includes the calculated stresses, the allowable limit stresses, and the resulting stress ratio. With that, all steps for modeling the welded cross-section and performing the weld stress design in our section are complete. Thank you for your attention, and now I'll hand it back over to Andreas.
Thank you, Sonja, for your nice presentation. At the end of the webinar, I have an additional hint for you. You can book our online courses, for example, the RFEM 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design, the Eurocode 3 course for the steel design, the Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. For more information, just scan the QR codes in the middle, or you can click at the buttons here. You can download the slides on the same website where you will find the recording and the models of today's webinar. In the next days, you will get an email with a link to that page. Okay, that's also all from my side for today. I thank you for your attention. Thanks to Sonja for your presentation. I wish all a nice rest of the day. Bye-bye.